I'll start just with a little description of what stuttering is. So I'm assuming that everyone's familiar with stuttering, although commonly people will say that they know what stuttering is, but they've rarely met someone who stutters. Actually, about 1% of the adult population does have a persistent stutter, but you may not know that somebody that you're familiar with does stutter, because there are lots of ways that people kind of manage their speech. So we understand stuttering primarily as a condition that affects the way that somebody's speech fluency proceeds. So they might experience repetitions in speech sounds that they've planned to say. They might find that they struggle and have kind of tension and involuntary pausing before producing a speech sound, or they might prolong speech sounds. So I've illustrated this here with a quote from B.B. King about the sensation that there's a fight between his thoughts and his speech patterns. So something is being planned and it's just not coming out in the planned way. Commonly though, for a person living with a stutter, it's a far more complex experience than just having these disruptions to the fluency of their speech. So having difficulties getting out the words that you want to say can have psychological consequences. It can make you feel really frustrated. And here's a quote from Emily Blunt, who I'm not sure whether you know. She's spoken quite openly about stuttering and that her stutter was more severe in her younger years. And here she's illustrating this feeling of being really frustrated that it was causing her to miss out on life opportunities. Also, it can affect language skills in voluntary or involuntary ways. Something that's really quite common in people who stutter is that they will avoid those moments by rephrasing, which is a really clever, and the speed with which someone can do this is really impressive. However, it can leave people with the feeling that they're never saying exactly what they want to say. So they might be using an alternative word that just doesn't convey the same meaning, which can be quite frustrating. So although that it supports the fluency of their speech, it doesn't really support their exact message. Okay, and on top of this, obviously we're all highly social animals, and speech fluency really is kind of a valued social currency. We make loads of judgments about people based on the way that they speak. And again, living with a stutter can involve a lot of stigma from our social environment, those who surround us, either people who we directly are in contact with, or the wider kind of societal messages around what a disruption to speech fluency means for somebody. So here's Bill Withers talking about that feeling of being disregarded, which I think, unfortunately, people still report fairly commonly. And all of these levels interact in a complex way in the life of somebody who stutters. So Joe Biden has been in the media a lot recently for choosing not to speak about his stuttering in the beginning of the kind of electoral campaigns in the States. And he has quite a direct quote about the interaction between some of the kind of muscular tension when he stuttered and a really intense kind of psychological consequence of feeling very ashamed. And this we can see is coming from the environment, so being the stigma brought by others, but also there's a high level of self-stigma in people who stutter too. So thinking kind of therapeutically for adults who stutter, particularly in the UK, we would try and use a very kind of multifactorial model of understanding someone's stutter, and also of offering therapy choices. So quite often people will use cognitive behavioural strategies as part of managing their stutter and trying to feel more positively about social interactions where their stutter is causing them some difficulty. There's also a huge amount of work to be done, obviously, with changing societal views of stuttering. But I'm going to be focusing on this middle part and specifically thinking about the speech motor aspects of someone's stutter. So for adults who stutter, there are ways that we can modulate the fluency of their speech. So someone might choose that as part of a package of therapy, they want to work directly on their fluency to be able to manage certain situations. However, the effectiveness of these methods are variable, and often they involve quite a lot of practice of something explicit that is very different from how somebody normally speaks. so it can affect their speech naturalness, particularly in the short term. It can also really affect their sense of identity, so it doesn't, although it might be successful, it doesn't sound like them. So although there's a strategy for reducing moments of stuttering, they might just choose not to use it because it's jarring with their sense of who they are. So there are reasons then to try and make therapies that are focusing on speech motor skills as effective as possible to try and address some of these issues that exist in current options for fluency therapy. Okay, I'm going to talk a little bit about what's going on in the brains of people who stutter then and how that differs from people who don't. So I've arranged this according to 3 kind of broad theoretical frameworks of understanding what's different in the brains of people who stutter. But you'll notice that there is quite a bit of overlap and there's no kind of real consensus on exactly what is happening. And it may well be that the same thing is not happening for everyone who stutters within their brain when they're speaking. But there is a consistent finding of a potential difference in integration of sensory and motor information during speaking. So behaviourally, there's this long-standing finding that if you change something about the auditory feedback to do with somebody's speech, for someone who doesn't stutter, that can really disrupt them and make them make speech errors. For someone who does stutter, it can actually make them more fluent. So you can change feedback by delaying it, by shifting the pitch. You can also enhance feedback by getting someone to speak in time with somebody else, which also has other effects that I'll go and speak about. I have a little clip here to show you of how effective this is for somebody who stutters. The key areas then that would be affected in the brains of people who stutter, the auditory cortex, so consistently that's been shown to be underactive when someone who stutters speaks compared to someone who doesn't. There are differences in the activity in the motor regions. So an area that I'll go on to focus on is the left inferior frontal cortex, so kind of ventral premotor areas which are really important for planning speech and also for processing feedback about speech to keep us on track. Also in the primary motor cortex, differences have been found. I'm being a bit vague about differences because the direction of those differences is not always consistent, but generally a reduction in activity is the more consistent finding. And also differences in activity in the cerebellum, which is also a part of the motor system that's very important in terms of kind of predicting feedback, sensory feedback. And here we tend to see underactivity when people are speaking fluently, but it becomes overactive during moments of stuttering. Okay, I did cover the brain there. Okay, next I'll move on to talk about another idea that's a bit more of a recent idea about what might be one of the mechanisms of stuttering. So there's a circuit in our brains which is right lateralized, so it involves the right inferior frontal cortex, which is kind of the matching homologue of this left hemisphere region that's really important for speech planning. It also involves an area deep in the brain called the subthalamic nucleus, and also the supplementary motor region. Some people will say the pre-supplementary motor region. So this circuit would help when you've planned a movement, but then you have to stop yourself. So this can experimentally be tested by either getting it works with any sort of movement, but typically people will have a manual task. So you would see an arrow which is prompting you to press a key, either on the left or the right of a keypad, and you go on and do this task. So typically you'll just randomly see lefts and rights, and then every now and again you'll hear a beep and you have to stop yourself. Or you could have a vocal version of this where you're seeing lots of words in this example, just made up words. You're saying these words as quickly and as accurately as you can, and then you'll hear a beep, have to stop yourself. So the performance of people who stutter has been shown to differ to people who don't stutter. And when we look at the activation of this network, it tends to be overactive in people who stutter. And it's been suggested that this might be part of the primary kind of characteristics of stuttering, that a person who stutters is excessively activating their stopping circuit, so they're inhibiting movement more than they should. And we see it more in speech because speech is more complex. We're not seeing it in other movements so much, but we can experimentally pick that up. Okay. And the third idea is around basal ganglia function. So this has come behaviourally from noticing differences, similarities between some of the features of Parkinson's disease and stuttering. So obviously people with Parkinson's disease are much more affected than people who stutter. However, there are some commonalities. So if a person with Parkinson's is having difficulty initiating a movement, for example, walking, if you give them an external stimulus like stripes on the floor, that they can use that external cue to help them move. And we see a similar effect in people who stutter when we give any kind of sensory stimulus. The example I'll show you here is an auditory stimulus, so a metronome beat. Okay, so again, this was highly effective with this man, and typically we see really strong kind of complete fluency or almost complete fluency, independent of how severe somebody's stutter is. The day 1 and day 5 will become clear later. I showed you this as an example of the rate with which we can use the metronome. So on day 5 here, and I'll show you it's day 5 of the intervention, this pace of the metronome was set to a kind of typical speaking pace, which kind of sounds quick, but he was able to manage this very easily. Okay, so there's not a huge amount of imaging evidence for differences in the basal ganglia, and it might be to do with difficulty actually imaging these quite small structures, but they do come up. So in meta-analyses, they're not coming up, but in several studies, over the years, we have seen an underactivity in the caudate nucleus and putamen, which are part of the basal ganglia system. And I'm telling you about these regions because I was particularly interested in them. And so they have guided some of the analysis of the study I will go on to show you now. So I'll move on to tell you about this randomized control trial that we did. So it used a method called transcranial direct current stimulation. I'm going to give you the most simplified overview of TDCS because there's a lot of ways that it can be used, and there's a lot of discussion in the field about effectiveness and how we can improve effectiveness. But the general principle is that we're running a really weak current between pads that we place on somebody's head. So these are electrodes. One has a positive charge and one a negative, and the current is flowing between them. And in the broadest terms, the pad that is the positive electrode will increase the resting membrane potential of the brain tissue as the current passes through. The pad that is the negative electrode or cathode will slightly downwards shift, so depress the resting membrane potential of the brain tissue as the current passes through. And what this does basically is kind of prime, under the positive electrode, kind of prime the brain to be active, and under the negative electrode, kind of dampen down the likelihood that it will be active. And the kit is really portable. It's really kind of tolerable, which is why it's attracted attention as a potential therapeutic kind of adjunct to behavioural therapy, so something that you can add on to improve outcomes. And there have been some positive outcomes. So I was most interested in outcomes around motor skill. So there have been studies kind of in both typically developing people and people who have either got a developmental or an acquired disruption to their motor system. The effects there have been quite promising. There have also been a number of aphasia studies with kind of mixed effects, but still also some promise. So that's why I was interested in it. And I used a design where we randomly assigned a group of men who started to either have real stimulation or a sham, where they didn't know and the researcher didn't know whether they were having real or sham stimulation. Sham stimulation just involves a really short period of stimulation. And they had an intervention over 5 days. I'm just going to focus on the primary outcome of this study, which was just counting the number of disfluent moments in somebody's speech in a reading and conversation task, and expressing that as a change in the percentage of disfluent moments in speech relative to a baseline period. So we measured this at baseline, and then our critical time points after the intervention were 1 and 6 weeks later. We had some other outcome measures as well, but I will not focus on those just to save a bit of time. So primarily we were interested in these outcome time points. It was also, as the first study using this method with people who stutter, we were interested to see how the effects of the TDCS developed over the course of the 5-day intervention. So the stimulation was focused on this left inferior frontal region, which we know to be underactive in people who stutter. And also we know that there's disruption in the connections between this region and others that are important for speech communication. The intervention we used involved this choral speech and metronome time speech, so 2 methods which will immediately induce a fluent mode of speaking. And we were interested in how that induction of a fluent mode of speaking in a very effortless way would be reinforced by the stimulation. So we deliberately didn't choose a more traditional speech and language therapy approach where we'd need to go through a period of practice before getting to a more effortless state of using the methods, which might vary between participants. So this meant we could just have a shortcut, immediately get people speaking fluently in all of the 5 sessions and see how that carried over. Our groups were well matched. We deliberately had people with at least a moderate level of stuttering so that we could have room to see some change. Okay, so first of all, looking at how these effects of the TDCS developed over the 5-day period. So here I'm showing you the change in fluency. So here, kind of lower is better. This is a reduction in stuttering. The grey lines are the group that received sham stimulation. So here, because these are just temporary and immediate effects, we didn't expect to see them evident in someone's speech, even measured immediately after practice. And that's exactly what we saw, both for the reading and the conversation. There was no change in speech fluency, so a baseline level of fluency immediately after each of these 5 days of intervention. The red line is showing the performance of the group who had anodal TDCS over the left inferior frontal cortex. And here we saw effects both in the reading and the conversation tasks, but the effect was more robust in reading, so it was immediately there and it pretty much just stayed there over the 5 days. Whereas for conversation, it took a little bit longer to become evident, but by the last day of the intervention, there was a clear effect of the brain stimulation. So we were critically interested in these outcomes at 1 and 6 weeks after the intervention, and here we see that there was this robust effect on both reading and conversation at the 1-week time point, and this effect persisted at 6 weeks, but was really driven by the reading task, which kind of reflects these patterns of development over the 5 days of intervention. Okay, to summarise what we saw in terms of how speech fluency was changing, we saw this significant effect during the 5 days intervention with anodal TDCS, and critically, we saw a difference measured 1 and 6 weeks after the intervention, which was more robust for the reading task. So what's actually going on in the brains of people who stutter following this TDCS intervention? To test this, we used the functional MRI task. I won't tell you the details because it doesn't really matter. There are 3 different speaking conditions which we used to reflect what people were practicing in the intervention, but actually there weren't interesting differences in the change in these 3 conditions. So I'm just going to show you collapsed across all 3 conditions. But basically we got people to speak in an MRI scanner. So they were reading sentences, and we used a rest condition where they were just looking at foreign text on a screen. And we analysed these data by focusing, so these 3 theories that I've told you about stuttering, we focused on the regions that are involved in these theories. So we used a region of interest analysis, which basically just involves making a sphere in that region. So we used the peak that had been shown in previous studies as the peak activation difference in people who stutter, and we just made a sphere around it and extracted the brain signal basically in that sphere to look specifically at the regions that we thought might be showing interesting change. So, starting with the region that we actually stimulated, which is in the left inferior frontal cortex, we actually didn't see any change here between the people who had the active stimulation and the sham stimulation. So here again, the active are in red and the sham in grey. So neither in the region that we stimulated or the right hemisphere homologue of that region. We didn't see any changes in the primary motor cortex either, or in the auditory cortex or the cerebellum. So that wasn't the most promising start. However, it might be that we're stimulating one brain region and actually the interaction with connected regions is more important. So moving on to these regions that are involved in the stopping circuit. So starting with the SMA. So here, again, nothing promising coming yet. However, when we looked at the right insula, which is part of this network, our more ventral sphere, so you can see here, one just here, showed an increased activation in the group who had received TDCS. So comparing after the intervention to before the intervention, there was an increase in activation there, and also in both of the regions in the midbrain. So in all cases, we saw increased activation, and this excessive inhibition idea is that the inhibition is maladaptive, so it's actually causing stuttering. This pattern is the reverse, so suggesting that actually increasing stimulation in these regions might actually be compensating for stuttering rather than causing it. And again, in both of our basal ganglia regions on the left and the right of the brain, so here the regions of interest are larger because we actually defined them just by the shape of the region, so we include the whole of the caudate nucleus and the whole of the putamen. And here we saw the same pattern, so an increase in the group receiving TDCS compared to the group receiving sham. So should we think of these differences as a normalisation, in inverted commas, of brain function? So we often think of therapeutic effects kind of behaviourally as we're helping somebody show a more typical pattern of speaking, and then when we're looking in the brains, we're potentially looking then for a typical pattern of activity to match that. So I'm showing you here data at the post-intervention time point. So this isn't changed, this is just how active these regions are at 1 week after the intervention. So I should mention first, I've not shown you anything pre, and there was an interesting finding in that I didn't find significant differences between my people who stutter and my control participants. So here in black, there is just a group of people who don't stutter, who are matched for age and gender. And at first I was quite worried that I wasn't seeing these kind of consistent patterns. And I'll go on to kind of discuss why that might have been, what's different in this group of people, and what do we maybe not consider in the previous research. But I'm showing you the post-intervention data because here I do see differences. And the consistent difference really is that I'm showing more activation in the group that received the TDCS, both relative to the group that didn't and also relative to the controls. So what I'm actually showing is a move away from the pattern of brain activity of someone who doesn't stutter. And this is associated with a positive outcome in terms of an effortless fluency. So these are the effects in this in regions related to inhibition of movement. And we see the same pattern in the basal ganglia. So here we see it in the putamen rather than in the caudate nuclei, but this same pattern of an increase in activation relative both to a group of people who stutter, who aren't having a benefit to their speech output, and also a typically developing group. So to summarise then what I'm finding in terms of brain differences is that we're getting a behavioural effect of improved speech fluency, and this is associated with some changes in the brain, which are within the stopping network, so this inhibitory motor network, and also in the basal ganglia nuclei. We're actually finding that overactivity of the stopping circuit might be involved in a compensation, so a successful compensation for stuttering, rather than a primary characteristic of stuttering. The effects that we're showing in the basal ganglia are consistent with previous theorising that the basal ganglia might not be being sufficiently activated in people who stutter. And also this pattern is in the same direction as previous studies that have used behavioural therapy but not brain stimulation. So there it's a consistent finding with other behavioural approaches. However, we're not really seeing a change in the brain that would be described as a kind of normalisation or move towards a typical pattern of brain activity. And one of the big differences in our study is that we deliberately chose people with a more moderate level of stuttering, and you would perhaps expect then to see a larger difference. And I don't have any definitive answers for you about why we're seeing less of a difference, but potentially our group really does differ quite considerably from a typical group who would be involved in an imaging study. So we're not just picking one end of a normal distribution, it's actually a skewed distribution. So most people who stutter stutter mildly. So it might be that mild stutterers are overrepresented in previous imaging studies. And there's also the issue that mildness, overt mildness, might not reflect just less moments of stuttering, but it might reflect less moments of stuttering due to compensations. So we're looking at a system that's kind of compensating, but perhaps in a maladaptive way, in that it's causing somebody quite a lot of stress and effort to maintain that pattern of speech. So that's something that I'd like to explore more. Of course, in this data set, it's not ideal because I've only got one end of the spectrum, but it might be interesting to look across a distribution of people who stutter and see if some of these differences are actually borne out looking at degree of covert strategies to manage stuttering. So we did find that TDCS was an effective method for increasing fluency. So that gives some promise, and we're currently looking at doing another randomised control trial. We're more than halfway through now. So it may be the case that for people who do choose to work on their fluency, TDCS could be something useful to apply alongside behavioural therapies. Also, the findings of these kinds of studies, both the stimulation, behavioural findings, and also imaging findings, may be quite important in terms of increasing our understanding of the differences in the brains of people who stutter, which are related to stuttering itself, to compensating in different ways, and to positive or negative fluency therapy outcomes. So I think it's a complex relationship which is potentially going to be supported by looking both on a behavioural level and on the level of the brain, and potentially getting larger data sets to really be able to pick out these patterns of change. So that's everything that I have to tell you about. I was talking very quickly because I realised I have more content than time, so I hope that was okay. But thank you very much. This is my due.